So, welcome back students. Basically in the last lecture we have just started symmetry based strategies, and we said that for symmetry based strategies, when you are trying to do a disconnection of a symmetrical molecule, and mainly we said we are dealing with symmetrical molecule which does have a well defined sigma v. Now, mainly we discussed couple of designed molecule like rho-10, 3 rho-10, 5 rho-10, those molecules, and we said in maximum cases we explore the redundant functionality, and also we said that maintenance of symmetry throughout the pathway is very important, and eventually we have tried to follow that guideline, that symmetry maintenance. The starting material needs to be symmetrical, or if the starting material is asymmetrical, it is always advisable to use those starting materials. So, symmetry maintenance is absolutely important for sigma v compound, sigma v containing compound, and we said that we are not going to discuss about the symmetry controlled reaction, which is the pericyclic reaction in this particular forum, because it is not it will take too much time. So, we are not going to discuss it. Now, we will keep on discussing the same strategies, and now here we will be trying to take some of the natural products which does have a perfect sigma v, and how we can follow this particular guideline, the maintenance of symmetry for synthesizing those molecules, or to provide a proper guided retrosynthetic disconnection for those molecules. In the very beginning we will talk about a natural product which is also a perfectly sigma v containing molecule, and the structure we need to be little bit careful. It is a cyclic ketone, and the molecule's name is civetone. Civetone was basically isolated from the civet cat, which is normally lives in the Himalayan region, high altitude region. Now, civetone, the molecule name is civetone. This is a perfectly sigma v containing molecule. The symmetry is there. Okay. So, now this is basically I said naturally occurring molecule, natural product. It is a natural product. So, it is not a designed molecule. As I said, this molecule is a perfectly symmetrical, probably the symmetry maintenance criteria we need to fulfill. And now definitely, as if you see the structural features of this molecule is basically having a carbonyl functionality, and now the left hand side and right hand side are basically having a equal number of methylene groups. How many? It is a 1, 2, 3, 4, 5, 6, 7. So, 7 methylenes left hand side, right hand side 7 methylenes, in between you have a Z olefinic unit. So, all together the ring size is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This is basically a large ring, it is 18 member ketone. The initial retro which was thought of for this molecule by doing a simple FGI, and the disconnection was proposed that the Z olefin which lies in the bottom part of the molecule can easily be constructed from the corresponding alkyne. This was usually proposed. So, if you have a simple FGI by using a hydrogenation with Lindlar catalyst, you will be able to do it. Now, alkyne, you may ask that, so alkyne is basically sp hybridized, and as the ring structure is quite big enough, means that this bond has to be linear. We wrote the bond in a bent fashion, but in reality this bond will be linear to fulfill the criteria of sp, and as this bond size is pretty much larger, this alkyne can be accommodated here. But for normal rings, like if you have a cyclopentane kind of ring, you cannot have a alkyne due to severe ring strain, because sp accommodation in a linear fashion cannot be done in this small ring system. But fine, nevertheless we will keep on using. Now see, the initial starting material is sigma v, this one also symmetry was maintained, symmetry was maintained. Now the next disconnection which was proposed or which was performed by the researchers, they proposed that if this alpha beta unsaturated ketone was used as a starting material, and then basically you can reduce this alpha beta unsaturated ketone to get this cyclic ketone. Now this part I will not write the CH2, this part I will not write the CH2, because you know that how many CH2s are there. So I will just put the alkyne here, this is the alkyne. So I said that if you have this kind of fragment with this CH2n, this is basically contains CH2n. How many CH2? 1, 2, 3, 4. So now basically you are having 1, 2, this CH2 is needs to be created. So this was done, then 1, 2, 3, 4, 5. So n is now 5. So here also you are having CH2n, n is 5. Now this alkyne as well as ketoolefin can be synthesized, people have been thought in a different way. Now this molecule is also sigma v, this is also sigma v. So now the next retro which was proposed, if you see the earlier intermediate which you basically propose, it is having a we will again draw it, it is basically having a diolefinic partner, and this end and this end are basically linked, you are having a acetylenic unsaturation here. Now I am saying that we will try to do a intramolecular Wittig reaction, to construct intramolecular Wittig, or you often talk about this reaction Horner-Wadsworth-Emmons reaction to construct this compound. Now the Horner-Wadsworth-Emmons reaction, probably all of you know, if you having RCHO, you react with corresponding phosphonate derivative in presence of a base. This reaction we have discussed earlier, and it is possible you can basically get the alpha beta unsaturated ester. This is a very known reaction, oil known reaction. Now here what I proposed, so now if you have, it is not a intramolecular Wittig actually, it is basically a intermolecular Wittig. We propose that, okay, so this part you will be creating and this part you will be creating. So this particular double bond, is coming from a Wittig, fine. So then I say that, okay, in between if you can put this carbonyl, and then the phosphonate is basically a bisphosphonate, you are using a bisphosphonate, something like this MEO-OMe. Now this bisphosphonate, bis-ketophosphonate, in principle having acidic hydrogen here which can be easily picked up by base. Now the central carbonyl of this ketone served as this CH, this CH is this CH, this CH. So this basically gives you 3 carbon. Now this carbon and this carbon is coming from the aldehyde. So now I am saying that if you having a this alkyne aldehyde and this part also this alkyne aldehyde, Now, this part basically I said is a CH2 5 in the earlier slide. So, if you have a base alkyne aldehyde, you do a Horner-Wadsworth-Emmons reaction, then you do the Lindlar catalyst mediated reduction here, and then you reduce this double bond completely. So, or initially you can reduce this double bond first and then touch the Lindlar one. So, this way basically you can do the synthesis. Now, coming to your remaining part. Now, see this molecule is a sigma V, this molecule is a sigma V. So, symmetry was maintained. So, now I am saying that probably this compound you can easily prepare if you have the required this kind of propagylic alcohol. Now, depending on the number of carbon, you can basically figure it out how it can be easily constructed, and then for this left hand side this is also similar kind of. So, you again put a so basically you need how many carbons? Basically you need 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, this X iodo or bromo. Now, this is Pg stands for the protecting group. So, this kind of compound can be easily prepared from corresponding 1,6 hexane diol by using protecting group chemistry, that you all know. So, what you do? You just create a carbon ion, react with this electrophile, and then you get this is 6, this is also 6. Then this Pg has to be removed, you oxidize this alcohol to get the symmetrical dialdehyde, fine. Then you do the Horner-Wadsworth-Emmons reaction. Now, once you do the Horner-Wadsworth-Emmons reaction, your next part is basically you have to do the first this particular double bond reduction. The double bond reduction can eventually be done without touching the triple bond. Mainly you can use a diimide reduction. So, diimide is a very selective reduction which usually do not touch the triple bond, and then once double bond reduction was done, you can touch the triple bond. So, in that way, but if you the take home message or the main point which you are highlighting is basically your symmetry maintenance. So, you see initial that bis alkyne aldehyde is having the sigma V, and remaining all the intermediates having sigma V. So, sigma V was basically maintained throughout the pathway, that is why you called maintenance of symmetry is absolutely important, and that is also give you a good guideline that how you can make your entire pathway. Now, if you go through the earlier lecture, we said that under this symmetry based strategies, we will try to focus mainly 3 or 4 different topics. We said we will be talking about maintenance of symmetry, which we have basically discussed, maintenance of symmetry, and then we say that there are examples which you have talked about molecules like adamantane and molecule like garudane, and also the naturally occurring compound civetone. Next we said that there will be 2 remaining points which will be need to consider. The another point which is very important, the next point, it is called local symmetry and pseudo symmetry. So, these 2 points now we are going to discuss. Now, as I said, local symmetry, the name implies a molecule or a particular segment of a molecule contains a symmetry, and that gives a local symmetry. And due to presence of the local symmetry, the entire molecule is not symmetrical, but like symmetrical molecule. That is why it is called a pseudo symmetry. And if I see, I'll give you a very standard example. We just didn't, I say we are having this kind of compound. I have drawn in a 2-dimensional way. So, I say this molecule is a perfectly symmetrical. Okay. There is absolutely no doubt about that. Now, I am saying I am drawing another molecule, and then I am saying that if this cyclohexane part having a Y functionality, this molecule now does not have perfect symmetry, because the presence of this Y functional group here makes the molecule not symmetrical, but still the cyclobutane part is symmetrical. So, now this is called local symmetry. The cyclobutane part which has the symmetry is called local symmetry. Eventually, presence of Y is basically the main disturbing factor. So, from a perfect symmetrical molecule, now the molecule you can call it as a pseudo symmetry or pseudo symmetric molecule. Now, sometimes there are many natural products which you will find that they belong to this class, pseudo symmetrical class, and for this the pseudo symmetrical molecule is always advisable if you can disconnect the pseudo symmetrical molecule to a local symmetrical molecule, or a, now local symmetry means this part is perfectly symmetrical. So, then our criteria of perfectly symmetrical molecule, where you said that maintenance of symmetry is strict advisable or strict criteria. So, now what we will be trying to do, we will talk about some example, and then you will find that how this local symmetry and pseudo symmetry is taking a lead role. The example will basically a natural product, and this natural product name is bisocalamic acid. You see its structure very carefully. The left hand side and right hand side of this molecule having a malic anhydride part, okay. And then this 2 malic anhydride part was joined. The left hand part was joined with a 3 methylene bridge, and the bottom part was joined with 2 methylene bridge. In the top 3 methylene bridge, in the center you are having a ethyl functionality, in the bottom hand side you are having a N propyl functionality. The stereochemistry was there, but we did not discuss about the stereochemistry. Now, this is a natural product whose name is bisocalamic acid. Fine. Now, if you now analyze the bisocalamic acid should be perfectly symmetrical like this way if there is no ethyl group here. So, minus ethyl, the molecule is perfect symmetry. Fine. Now, as ethyl is there, the molecule becomes pseudo symmetry. So, now we will try to analyze that how this molecule can be retrosynthetically disconnected, and it was shown that this molecule can be synthesized by or from these two intermediate. So, one of the intermediate is pseudo symmetrical intermediate and one of the intermediate is local symmetrical intermediate. Now, we will explain how. Now, this molecule I said this part all almost symmetrical. So, this part is having local symmetry. The central part seems to be symmetrical except this ethyl group. So, now I am saying that you can basically make this molecule through these two starting material, where this one is perfectly symmetrical and this one is having local symmetrical. So, a local symmetrical unit and a pseudo symmetrical unit contains together to give you a pseudo symmetrical molecule. Now, the disconnection part we will now try to focus. At the very beginning we said that the succinic anhydride this malic anhydride part can easily be constructed through a oxidative ring cleavage this is oxidative ring cleavage of this aromatic nucleus, like having 1,4 dimethoxybenzene. The remaining part of this molecule will remain similar. We will put a ethyl group here, we will putting a N propyl group here. So, this is fine. So, initially this is again a pseudo sigma V or pseudo symmetrical, right. Now, I am saying that this ethyl and this N propyl we need to introduce. So, next what retro was proposed, the central thing, the ethyl group will be introduced, and it has been proposed that ethyl group can be introduced from a cyano group by a normal FGI. Now, what are the reactions we will be doing it here? Cyano group reacting with a methyl magnesium iodide will give you COCH3. Then this COCH3 will be converted to corresponding ethyl by a Wolff-Kishner reduction. We are not going to discuss the forward path, as it is very straightforward. So, now the next retro which I am now proposing, it is bit different. We are now saying that the next retro which will be now all the other parts will be remain similar. The two aromatic ring is similar, and then we are saying that this CN is there, and we will be saying that let us formulate this as a ring. Now, the intermediates, earlier one is having pseudo sigma V, this is also having pseudo sigma V. So, basically symmetry was kind of maintained, and now this molecule is basically having this part is local symmetrical, this part is pseudo symmetrical. Now, why you have to, this is basically a normal FGI, this is normal FGI. If you just reduce this double bond, you come to the earlier intermediate. Now, this particular fragmentation which was proposed now, it is very interesting, and this is the limelight of the entire synthesis or the main highlight of the synthesis. This will explain in detail how this mechanism takes place. So, what you say, if you have this particular intermediate which we are proposing here, this intermediate can be easily converted to this intermediate. Now, how? I am saying that I am just writing in this way, that if you convert this ketone to corresponding oxime. So, oxime was means now you do a Beckmann type of rearrangement. So, means this oxime will be first converted to corresponding this OH2 plus, and then this will go. So, you have a electron deficient nitrogen. Now, here if you see this compound, you make a oxime, and then once this OH2 plus goes up, you will find that this bond fragmentation will basically give you a positive carbonium ion here, like this particular bond will fragment, or it so in this way basically if it goes, it puts its charge here to give you a nitrile and fragments in this way. So, this fragmentation we are talking about. It is basically a Beckmann type of rearrangement, but it is called Beckmann fragmentation. Now, why this carbonium ion is formed? Because this carbonium ion now which is forming here is extremely stabilized, because it is a benzylic as well as tertiary. So, now this thing is basically cleaving and you get a cyanide here. So, this C stands for cyanide. Okay. So, the Beckmann fragmentation is the crucial. So, we now say that is a very good FGI, and the reaction is Beckmann type of rearrangement. You can think about Beckmann fragmentation, you can just call it fragmentation. So, now we have to complete the synthesis. Now, you see the starting material can be easily correlated. Now, our starting material can easily be correlated. So, OMe, and the starting material which was given as the initial lead can now be linked, So, this part you are having this corresponding benzyl chloride. So, what we say? We say that this ketone does have a this acidic hydrogen as well as this acidic hydrogen. So, you do a successive round of alkylation, one with this side the thermodynamically controlled and this side the kinetically controlled, you basically get this double alkylated product through a FGI. The Beckmann fragmentation was pretty important, which will be now just giving you the mechanism just for a very simplified version. We say you have this particular compound. So, you have this Beckmann rearrangement which you are proposing, or it will basically takes place, and then you have this, because the drawing has to be little bit bigger, otherwise the fragmentation you won't visualize clearly. Okay. So, now you say initially this goes up OH2 plus, okay, and then once this goes up, it will try to fragment in this way or this way. Now, this way fragmentation give you a positive charge here, and this way fragmentation will give a positive charge here. So, this fragmentation will basically give you OMe, this part, and then your cyanide now goes there, isn't it? So, your OMe. So, fragmentation basically means this bond puts all these electrons through this double bond. So, C triple bond N is formed. Now, you will basically having this carbonium ion. This is absolutely stable carbonium ion, benzylic as well as tertiary. Now, you are having hydrogen. So, this hydrogen will give you the eliminated product, which is one of the intermediate we proposed, and this is also the sigma V or pseudo sigma V intermediate. Now, we are basically yes. So, this was the intermediate which was earlier proposed in one of the steps. If you see, the symmetry part was strictly maintained. Now, what you do? Once you have this earlier intermediate, you first do a methyl magnesium iodide, as I said, you do a Wolff-Kishner type reduction and also you do a hydrogenation. So, once you do this 3 FGI together, you probably end up with the main core of this molecule, where only thing you need to do it, the oxidation of this aromatic electron rich aromatic part, where you are having this 1,4-dimethoxybenzene. Now, this intermediate is sigma V or pseudo sigma V, because this intermediate is pseudo sigma V, except if this is N propyl can be removed, the molecule is perfect sigma V. This part I say local symmetry, this part also I say local symmetry. So, local symmetry element are there. Okay. Now, the remaining part what was done actually normally this kind of transformation they used a late tetraacetate and do a oxidative deamination. First probably initially you do a BBr3 mediated demethylation of both the aromatic ring. So, you will be having OH first, which will basically we will use this one little bit later on. So, BBr3 first demethylate the OH, this part is there, and then you write this OH and OH. Okay. Now, the oxidation part. So, oxidation you are using a late tetraacetate to basically give you the corresponding quinone, this quinone, this quinone. So, use this quinone, and then the reagent which was used is a hot KMnO4 solution to basically clip this double bond, to clip this side double bond, and then cleavage of other things also, means it is like a oxidative cleavage, and then what you basically get, you get this dicarboxylic acid. So, this now undergoing cyclization with phase of acetic anhydride, and then you get the parent compound whose structure is, you basically have this malic anhydride part which you are talking. So, this malic anhydride is, you write this way, the left hand side, you write the right hand side in this way. Okay. You have this ethyl group, you have this N propyl group, and this is your target molecule. So, the particularly this if you do not consider the symmetry part also, the synthesis is very unique, because you did couple of functional group interconversion, and the key transformation is here the Beckmann fragmentation. It was absolutely brilliant, and the Beckmann fragmentation will definitely give you the particular product what are looking for. Now, so probably we will stop it here, and next lecture we will try to continue on the similar topic, and how we can basically use the concept of local symmetry and pseudo symmetry to disconnect some of the target molecules, and see how the guidelines which you have earlier demonstrated, we can basically follow those guidelines in a sequential manner. So, okay, have a good time, goodbye.